All right, so here we go. So the idea here is we have a car. It's being pushed, and this is question 6. And we're going to treat the initial 6,000 joules that are transferred into it as elastic. And what's going to end up happening is this gets converted into, we're told there's movement and there's dissipated. So we're going to have kinetic energy and some dissipated energy as well. So keeping this in mind, we'll set up our equation as E elastic equals E kinetic plus E dissipated. And we want to know the speed of the car. So let's be kind of clear here. We may not need to use all of the equations that we have. We want to know the speed. And we're just going to do the bar graphs. We won't do energy flow diagrams, so none of this is needed. Now, in fact, I'm just going to fill this in a little bit more carefully, like this. So I don't even want to look at that circle. Just keep it out of the way. And then the idea here is with this problem, now we want to get the speed. So we have 6,000 joules initially. I don't need to know the spring constant. They didn't ask me for it, so I'm not going to use it. Equals 1/2 mv squared plus the 2,000 joules that's dissipated. So we have 4,000 equals 1,500 times a half, because that's the mass, times v squared. So we have 4,000 equals 750 v squared. So that's going to be 400 divided by 75 is v squared. I'm going to do a bit of simplification here. So this is me just doing some math. So I'm going to divide by 25. So that's 1 times 25 is 150 times 6. 16 divided by 3. So v is the square root of 16 over 3 when I simplify. When I actually get the v that you care about is going to be 2.3 meters per second is what I'm getting for the speed. That's the answer. All right. Now, the next question, I actually had us do this in class, but this is a totally valid question for me to ask. We're going to compare two situations, and we're going to look at some ratios of quantities. This is a really good question for us to be doing because it forces you to use all the stuff we've learned, but in a little bit of a different way. So, each of these masses is 1 kilogram, one's at 20, one's at 10, and we want the ratio of EGB to EGA. This is one of those things where all you have to do is follow the directions. Determine this ratio. So I need a number for this, and I need a number for that. And I'm going to go ahead and do that. So EG at B is going to be EG at B is going to be MGH at B, and EG of A is going to be MGH of A. So now I put in my numbers, 1 times 10 times H at B, which is 20. By the way, G is 10, so I expect you to instantly see that you put 10 in for G. We've gone over that a lot in this class. And this is 200. And then MGH at A is 1 times 10 times 10, and that's 100. So the ratio, EG over B divided by EGA, is going to be 200 over 100, which is 2. Some of you said, oh, wait, the H, some of you said, oh, yeah, it's like 20 over 10. So I'm going to tell you something right now, okay? If you write 20 over 10, that is wrong. You can't just compare heights. It has to be energy. So, again, this is one of those questions where you haven't done a question like this before exactly. But I do expect you to be able to use physics that you've used in the past and algebra that you've used in the past in order to be able to creatively come up with some new ways of looking at things, because all of this is based on old stuff that you have learned. Okay, so I do want to see how you can apply this to a different situation, and that's absolutely something that we test in physics and are allowed to test in physics.